Okay, with another example of the weak acid with strong base titration, I'm going to show you one more. It's just, essentially the same reactants. It's going to be potassium hydroxide instead of sodium hydroxide, but the numbers are going to be different in this example. And by changing the numbers, that changes the approach we're going to use for doing the calculations. So let me bring this up. Here we go. Okay, so same problem as the previous example. In this particular problem, we have 51.4 milliliters of 1.100 molar hydroxylic acid, HN3, 0.9700 molar of KOH. The pKa of hydroxylic acid is 4.72. We want to calculate the pH of the acid solution after the chemist has added 46.7 milliliters of the KOH solution to it. Again, for advanced students, the final volume is the initial plus the volume of the KOH that we added. Round your answer to 2 decimal places, okay? So it looks very much the same, but it turns out the numbers make a difference. So what I'm going to do is I'm going to rewrite the equation again. So HN3 is our acid. And here we're going to react it with KOH, not NaOH, but KOH. You know, for most purposes, KOH and NaOH are essentially interchangeable. They're both strong bases. They both form hydroxide. So again, we get water, and then here we're going to get potassium azide, N3, okay? So, you know, going through the calculations of millimoles, I'll do that here. So the calculation of millimoles for the HN3 is 51.4 milliliters times 1.100 moles per liter, right? Remember, I said in the previous video that using millimoles is really useful in these titration problems, so try to get used to it. So 51.4 times 1.1 is 56.54 millimoles, right? Because again, you know, what happens is the liters cancel, but you still have the milli there. So it's just millimoles. And then let's calculate millimoles of the KOH. So the KOH is 46.7. And here the concentration is 0.9700 moles per liter. So 46.7 times 0.97, and you get 45.299 millimoles. I actually calculated these before, but I'm checking just to make sure I get the same numbers. So our initial amount is 56.54 millimoles here, and then 45.299 millimoles here. This is zero, right? There's none of this initially. Water, there's water in there, but we're not going to worry about water. I shouldn't use X because sometimes that means something different, right? It's algebra, right? So now what do? We subtract the smaller number from the reactant side, right? Limiting reactant. The limiting reactant is the KOH. That's a smaller amount. So we're going to subtract 45.299 from both of them. But we're also going to add it on the right side, the product side. Sorry, I'm writing this incorrectly. Okay, so what happens? This goes down to 0. This one goes up to 45.299. And the HN3 is not going to be 0, right? It's going to be some number, 56.54 minus 45.299, then you get 11.241. Okay, 11.241. Okay, so now how are we going to approach this? You know, remember in the previous problem, we had leftover base, strong base, and we had conjugate base on the product side, the NaN3. In this case, it's KN3. So we have a base and an acid now, right? But keep in mind, what we have here is a weak acid. And this is its conjugate base. Remember, the conjugate base is you take your weak acid, you take an H plus off of it, you got your conjugate base. That's exactly what we've done. We've taken off the H plus from the N3 minus, replaced it with a K plus, and so we have a conjugate base. Now, here's the cool thing about this particular calculation. So I'm gonna circle these two numbers here. Weak acid conjugate base. There's a calculation we can do for pH. It's the pKa of a weak acid plus the log of the concentration of the weak acid, of the conjugate base. Divided by the concentration of the weak acid. Some parentheses here. Right? Isn't that right? If you have a weak acid and you have its conjugate base in the same solution, we can use this Henderson-Hasselbalch equation. Okay, and that's how we're going to do this. So we already know the pKa. It's 4.72. And then we can add the log. Now, we don't have the concentrations, we just have the millimoles. But remember, concentration is moles over liters, or if you want to have it in it could be millimoles over milliliters, right? Millis will cancel. But in the numerator, we would take the millimoles of the conjugate base, the KN3, and divide that by the total volume, right? Because it's in this mixture now, right? You've mixed everything together. So everything's all together. So you're going to find that concentration by dividing by the total volume. And then you're going to divide that down here by the concentration of the weak acid, which would be the number of millimoles of the weak acid divided again by the total volume. So here's what happens. You end up with millimoles of the base divided by milliliters of the solution in the numerator. And then in the denominator, you have millimoles of the acid divided by milliliters of the solution. And what happens? The milliliters of the solution cancel. So you're just left with millimoles of the base over millimoles of the acid. Well, the millimoles of the base are 45.299. And the millimoles of the acid are 11.241. Okay, makes it very simple. So that's another advantage of just like keeping everything in millimoles. Just cuts out a lot of the details of the calculation. So 45.299 divided by 11.241 is 4.029. So the pH would be 4.72 plus the log of 4.0298. Okay, that's that ratio in the parentheses. So if you take the log of that, you get 0.605. I'm going to put an extra digit there. We don't need to. And so if you add that to the 4.72, you get 5.33. 2 digits past the decimal point. Okay, 5.33. And there's your final answer. So notice, notice how different this happens to work out, right? In the previous example, if you watched that video, what you saw was that we had excess base, strong base, that dominated the pH. But here we had excess weak acid. So with the weak acid and the weak conjugate base, there we use the Henderson-Hasselbalch equation. So really be very careful about these calculations. Go through it step by step. Find the number of millimoles of each. Go through the equation to figure out how much is left over of each, and then pick what you're going to do in terms of your approach for the calculation of pH.